Hello, everyone. We'll get started here. I hope you're doing well and enjoying your week. This week we're going to be talking about synchronization and deadlocks. Before I get into the materials, I just wanted to let you know, in case you didn't notice, I do have a new discussion board out there called Resources. And I'm starting to use that discussion board to post different resources that may help you with some of the materials in this course. So I have some things out there to help you with Java. I have some videos that I'm going to post probably sometime today that'll help you with some of the materials in this week's assignments. Simply because the videos are visual. So if you're more of a visual learner instead of, reading or whatever, the videos may help you kind of see things from a slightly different perspective. So I just wanted to make you aware of that. The first thing that I want to do is go through the week 2 and week 3 assignments. The week 3 assignments, if you handed it in on time, I did grade those, so you should be seeing your grades on those. The week 2 assignments, I plan to get through today. We'll see how my day goes. But I really would like to get those out of the way as soon as I can. And then anything that came in late, I will grade after I get this other grading done. So just so you know, I'm trying to get things done as quickly as I can, but there's been so much churn with, people needing to resubmit assignments and the whole thing about plagiarism and so forth that I've gotten a little behind on the grading, but I hope to get caught up here soon. So the first question that you were asked in week 2 was to describe the actions taken by a kernel to context switch between processes. And this was actually a fairly simple question because you could find the answer directly in your book. Okay? All you had to do was kind of explain to me what this diagram was telling you. And the important things are that when it's going to do a context switch, and the CPU will be switched to another process, the system has to save the state of the old process and then reload the state of the new process. Okay, so those are the 2 important points that you had to have in your answer. Okay, there are some other things that you could have included, but the important thing was understanding that the first thing it had to do is save the state, save whatever information it needed to in the PCB for the first process that was running, and then reload the information of the new process. And I think most of you did pretty well on that, at least the ones that I've looked at so far. Are there any questions on that? Okay. The next exercise was to explain the circumstances when the line in the code marked printf line J was reached. And this was a fork and exec example, and your book actually went through a fork and exec example, and so all you had to do is kind of follow along with that and realize what was going on. Plus the code had comments in it that could help you. The important points in this question were to realize that the printf line J would only be reached in the child process, okay, because that was in the part of the code where I was looking at the process ID and realizing it was a child process. So that code would be reached only in the child process, and it would only be reached if the EXLP failed. Now the EXLP, if you remember any of the exec commands in a Linux system, are going to load in the new content for the process to execute. So if the exec LP succeeded, it would never get to that printf line J. It would only reach it if the exec LP failed. So those are the important points in that question. Any questions on that? Okay. Now this was the one that gave people the most difficulty. This was the exercise that talked about the fact that Linux didn't distinguish between processes and threads. They treat them the same way. Linux calls them tasks, but in XP or Solaris, some other operating systems, processes and threads are treated differently. And the question here really was, contrast these two approaches for modeling processes within the kernel. Okay, so that was the question that you were supposed to answer. Now for this one, there was a lot of different answers you could have had. And some of you obviously did quite a bit of research looking into how Linux handled processes and threads and how Windows handled processes and threads. And then you compared the two. And that was really what I was looking for in this question. So in your answer, some of the key points that I was hoping to see was that in Linux, it might be simpler for the schedule to treat a thread, it's like a tongue twister, to treat a thread as a process. In other words, it could use the same scheduling algorithms and whatever that it had for processes and threads. Okay, so that would be one way that the kernel in Linux would be different from the kernel in Windows. Okay. Another way that the two are different is that the actual process control block is simpler. Now Linux actually calls a PCB, a process control block, a task structure. And because the threads in Linux have their own task structure, it's not necessary for the task structure of the main process to have pointers to all the threads. They're just kind of treated as equals in the operating system. So the PCB would be simpler in a Linux system. And this has kind of advantages and disadvantages. One of them that some of you pointed out was that accounting for the resources might be more complex in a Linux system. Because if you think about it, the system's going to have to look at different PCBs, different processes, and determine which ones belong together because they're threads of the same process. Okay, so accounting for resources, a lot of times in an operating system, you're looking at limits. You know, how many files can a process have open? How much memory can be allocated to the process, and so forth. So what you want to do is, in a Linux system, is make sure that you're looking at all the threads that belong with a process or are associated with a process, to determine whether any of these limits have been reached. Okay, so not having the thread pointers in the PCB might make it harder for the operating system to do this type of accounting. And so then, of course, the points about Windows are the exact opposite. In Windows, the process control block may be a little more complex, but it makes it easy to track the shared resources. Remember, in a process control block, part of the process control block itself is to hold the resources being used by a process. So one process control block in Windows can hold information about all the different resources that are being shared by all the threads. So it's much easier then to account for the resources in a Windows system and impose limits. Okay? So that's kind of what I was looking for. I mean, some of you gave me a lot more information about the Linux operating system versus the Windows operating system, but really I was looking for specifically how is the kernel affected, not how the users are affected or how the mapping between user threads and kernel threads and all that. That really wasn't part of this question. Any questions on that? I know now that I give you the answer, it looks a lot simpler than it probably did when you tried to answer it yourself. Arwa, did you have a question? Oh, okay. I just thought, oh, I see your check mark was everything's good. Okay. All right, so let's move on then. And these are now your week 3 questions. And these took a little bit of thought. This question was, consider the exponential average formula used to predict the length of the next CPU burst. What are the implications of assigning the following values to the parameters used by the algorithm? So the first part of the question said, if alpha is equal to 0 and tau sub 0 is equal to 100 milliseconds, what are the implications? Well, one way you could figure this out is by actually running through the formula a number of times and see how it behaves. So what I did when I solved this problem is I said, okay, they're not giving me any value for T0. Some of you were okay with that. I like to give myself a value because I work better if I have real numbers to look at. So I made up a number. I said, okay, I'm going to pretend that my initial CPU burst was 5. So then I simply went through the calculation and I said, okay, I'm going to substitute in for T sub 0 or tau sub 0, which would be T sub n in this part of the equation, and I'm trying to calculate tau sub 1. Okay, so I just substitute it all in, and I get alpha, which is 0, times my most recent CPU burst, which is 5, plus 1 minus alpha, which is going to give me 1, times my prediction, which was 100. So if I go through that whole thing, calculate it out, I get 100. Okay, so that gave me one idea. The next idea was to say, okay, well, it looks like it's going to be 100, but I don't know if that's always going to be true. Okay, so again, some of you could look at the formula and you'd see that, but for me, I need to work it all out. So I went through it again. I said there's no value for T1 again, so I'll pick a number. This time I'm going to pick a big number. Say if my latest CPU burst was 250, what answer is it going to come up with? And I went through the calculation again, and it still came up with 100. The third time, still came up with 100. By this, I'm feeling pretty sure that no matter what happens, it's going to come up with the answer of 100. So my answer here was that it always predicts 100 because the weighting factor is 0. So there's no weight given to the recent behavior or the past history of the process. Okay, it's always coming up with 100. Okay, Nada, I don't know how you would have gotten 10, because if you look at it, if alpha is 0, then it doesn't really matter what T sub n is. That's going to be 0. But tau sub n is 100. So here I have 1 times 100, and I always get 100. I assumed values. I didn't have to. You can kind of look at this and see that even if you don't have a T sub n value here, this calculation, alpha times T sub n, is always going to be 0. Okay, I assumed values. And when you look at the example in your book when it went through this, they just gave you values for the CPU bursts. And you could assume those because you don't know what they're going to be, and they could be anything. Some processes are going to use the CPU for a long time, some for a little time. So I'm just working through the algorithm with some examples. What happens if it's only a little time for my CPU burst? What happens if it's a long time for a CPU burst? And that's how I went about solving this problem. The second part, again, I did it the same way, worked through all the math, except now alpha was close to 1 and tau sub 0 was 10. Now this gave me more interesting results. Again, I like to work with real numbers because it makes it concrete in my mind. And so I picked 5, saying, okay, I'm going to assume my first CPU burst was 5. I went through the calculation, and I hope my numbers are right, and I ended up with a prediction of 5.05. Okay, so I'm thinking to myself at this point, okay, it looks like the most recent CPU burst is pretty important here because my answer was pretty close. It was a lot closer to my most recent CPU burst than it was to my original predicted value. Okay, so that's kind of what I started looking at. And if you look at the formula, that makes sense. Alpha is almost equal to 1. So alpha times T sub n is going to always give me T sub n, and then, or something very close to T sub n, I should say. And then 1 minus alpha is going to be pretty close to 0. So that's going to give me a small number. So now I know that the weighting is weighting my most recent CPU burst more heavily than the predicted CPU burst. So I go through the calculations a couple more times. I pick again 250 just to see what it does with a big number. And I end up with something that's very close again. And then I do it the next time where now my prediction is big. It's 247.55, but my burst is small. And I go through all this again, and now I come up with a small number. Okay, so what I'm noticing is that the actual behavior of the CPU bursts in this process is given more weight than the past history. Because this part of the equation is how it's weighing the most recent CPU burst, and this part of the equation is weighing the past history, the past predictions that have calculated in it the actual CPU bursts. So my answer for this one is that the most recent behavior is given more weight than the past history, so the prediction's always going to be close to the previous actual burst. Okay, that makes sense? Again, I know once I give you the answer, it probably does make a lot more sense, but it is hard to figure this out for yourself. That's why for me, it was easier for me to actually go through this equation and figure out what was going on. Okay, now we had another question that was about preemptive priority scheduling and changing the priorities. Okay, and remember in these questions I wanted you to not just give me the answer, but explain the answer. So the first part of the question is, what is the algorithm that results from beta being greater than alpha being greater than 0? Now there's a couple things to know here. Beta is the value that's given to, or the change that happens to the priority when a process is running. Alpha is the change to the priority when the process is in the ready queue waiting for the CPU, and they all start at 0. So what this tells me is that the process, the priority of a process that's running is greater than the change in the priority of a ready process. So that means that something that's running, its priority is going to keep going up, up, up at a faster rate than the processes that are sitting in the ready queue. Okay, and they're greater than 0. That's why they're increasing. So once something gets allocated the CPU, it's always going to be the process with the highest priority until it's finished. So the process that's currently running will keep running until it's finished, and that's a first come, first serve algorithm. Okay, so that's kind of what I was looking for in the answer, knowing that it was a first come, first serve algorithm, but then explaining why based on the alpha and beta values, or the relationship of the alpha and beta values. The next question was kind of the opposite. Now it's saying that alpha is less than beta, and they're both less than 0. Okay, so now they're going to be decreasing the priorities. So the highest priority they get is 0, and then it'll be decreasing. Now the priority of a running process is going to be lowered more quickly than a ready process. Okay, because this could be, let's say it's a -10, and this is a minus, alpha might be a -10, and this might be a -1, for example. So the priority of the running process is going to be lowered very quickly. But a new process coming into the system never had its priority lowered, so it starts at 0. So what's going to happen is that when a new process enters the system, and this is a preemptive priority scheduling algorithm, it's going to preempt the process that's running. So all the latest process that comes into the ready queue is going to preempt whatever's in the CPU, whatever is allocated the CPU, because the process that's allocated the CPU, the process that's running, its priority has already been decreased. Okay, so that's a last in, first out algorithm. The last process that comes in is the first one that goes out. Okay. Any questions? All right. So let's move on then to this week. And a couple things that I want to point out to you. Your exercises are due on Sunday, and I changed one of the exercises. I switched, it had been originally exercise 7.8. I made it 7.7. Exercise 7.8 asked you to do a proof, and I felt that exercise 7.7 would be a little easier for you to do. So I changed that exercise. If you really want to do the proof and hand in exercise 7.8, feel free to do so, but I think you'll find exercise 7.7 a little easier. Answer the questions fully, and make sure they're your original work. Okay, I'm still seeing problems with that, you know, people are looking at the answers that they acquired somewhere. And I will be giving zeros out for if you turn in something that, to me, it's obvious that you looked at the answer and just changed a few words or whatever to come up with your answer. So make sure they're your original work. Get out of the habit of looking at the answer and get into the habit of doing the work yourself and working through the problem. Now, one of the things that I was also going to try this week is these are fairly short answers. And so one of the things that you can do when you submit your assignment is, instead of handing in a Word document, you can submit it using there's a text submission when you go in to submit your assignment. If you just want to type your answer in there or copy and paste it into there instead of actually attaching a Word document, feel free to do that. I'll get to the other your question in a minute, Sahar. I just want to make it clear that, this week what I'm going to try is letting you just put your answers in the text box instead of attaching a document, and see if I can get the grading back to you more quickly. Because when you attach a document, I have to download all the documents, I have to do the grading, I have to put the grade in the document, upload it back, and it's click, 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 wait for it to download, wait for it to upload, and everything else. Siham, you can do both. That would be fine. I'm just trying to make this be a faster process for both of us. So if you've worked on the assignment and you're ready to submit it, you could submit it as a Word document, or if you'd like to just submit it as text, you can do it either way. Okay? So I just thought that might simplify the process for us. Okay, now, this next thing, some of you may have just realized this for the first time because I didn't put this in the announcement for the week. There's a paper that's part of your weekly instruction, and you're supposed to read the paper and write a 300 to 500 word response. Now, what Sahar noticed right away is that it's worth 0 points. So do you have to do it? Well, obviously, you don't have to do it if it's worth 0 points. Okay? This is really meant to be an exercise in learning how to read a technical paper critically. So read the article and then summarize it in your own words. What are the key points that you found in this article? What did the authors find? What was kind of the point of their paper? What were the results of the work that they did? And then do you agree or disagree with the findings? So what we're trying to do in this exercise, and it has no points, so it's not going to hurt you if you try it and you don't do well on it. I mean, that's kind of why there are no points for this. But if you want to do this, this will help you as you start moving into, upper level courses, graduate level courses. If you want to go on for a PhD, you'll be doing this kind of thing all the time. Okay, so it's kind of a good thing to start learning how to do now, especially since there are no points, and so you won't be penalized if you don't do it well. On the other hand, I do understand that you're all very busy and there is a lot of required work to do in this class. So if it comes to Sunday and you haven't even had a chance to do that, I totally understand. I won't hold it against you, okay, if you don't do this assignment. Okay, is that clear? So that's kind of why I didn't put it on the announcements, because I didn't want you to, get totally overwhelmed with how much work there was this week. And, okay, Hala asked a question. This is all great, but is it okay to send it after Sunday? For these, yeah, I'll accept these pretty much any time because you're pretty much doing this work for your own benefit. Okay. The other thing is, since you don't get points for it, it may take me a little longer to get around to giving you the feedback, but the feedback's not time critical. It's kind of like you want to do it, to see how you do on it. I want to give you feedback to help you, but it's not going to be the top priority for either one of us. Okay, understood? Is that understood? Okay, great. Okay, so let's move on then to the things that we need to talk about for this week, and I'm going to go through these pretty quickly because we only have about a half hour left. But one of the main topics for this week was synchronization. And synchronization is when cooperating processes share an address space, if they're both trying to access that address space, there may be an inconsistency. So what we have to do is synchronize the processes to avoid this inconsistency and make sure that only one process is accessing the shared data at any one time. Okay, so when I say process here, I'm talking about it could be a process like we talked about earlier, or it could be a thread. Okay, because a thread is really just part of a process. So I'm talking about either way, we have to make sure that we're synchronizing. You can think of synchronization as forcing the processes to take turns when they're sharing a resource. Okay, you want to make sure that one is totally done with it before the other one tries to use it. So you're forcing them to take turns. A race condition occurs when multiple processes access and manipulate the same data concurrently. Okay, they're kind of in a race. Whoever gets to it first, that's going to change what the second one sees, and that's why it's called a race condition. So the results with a race condition are dependent on the order in which the different processes are run. Okay, so we know from our scheduling discussion the ordering in which processes and threads are scheduled depends on a lot of different factors. If we have a preemptive kernel, it's subject to many race conditions when it's accessing the data structures it uses to keep track of the files being used, the memory allocation, the list of processes that are either waiting or being worked on, interrupt handling. There's a lot of conditions where different data structures can be subject to a race condition. Even in your own code, when you're writing multi-threaded code, you can have race conditions, and because you may be accessing different or the same data into different threads. And actually the programming problem that you have to do is one where we're going to be trying to avoid a race condition. There's a classic problem that I like to use when talking about race conditions because it kind of simplifies what's going on, okay? And it's called the too much milk problem. And here's what's happening. Here's our race condition. Miriam, let's assume that Miriam and Nadia are roommates. So Miriam comes home. She sees there's no milk in the refrigerator. So she goes to the store. While she's at the store, Nadia comes home. She sees that there's no milk in the refrigerator. In the meantime, Miriam is at the store and buys milk and is now coming back home when Nadia decides to go to the store to get milk. Miriam gets back home. In the meantime, Nadia is at the store buying milk. Miriam puts the milk in the refrigerator. Nadia then goes back home, puts the milk in the refrigerator, and now they have too much milk. Okay, so you see, you could look at these, they're both doing the same thing, so they're like two threads that are doing the same thing in a process, but depending on exactly when these two threads run, there might be 1 quart of milk in the refrigerator, or there might be 2 quarts of milk in the refrigerator. Or you probably do liters, but we do quarts in the United States. Okay, so this is a good example of a race condition and how you end up with different results. Now, if Miriam arrived home and there was no milk in the refrigerator, then Nadia arrived home and saw there was no milk, they might talk about it and said, oh, who's going to get the milk? And only one of them would have gone out for milk. Or if Nadia arrived home after Miriam got back from the store, Nadia wouldn't even have considered getting any milk. So you see, just depending on when Miriam and Nadia get scheduled in the CPU, will change the results of what happens here. And that's called a race condition. Okay, so I like this example. It's a classic example that's used in computer science to explain what a race condition is. you're going to be looking at race conditions in exercise 6.1. Okay, and here, this is again a common example that's used for race conditions because it is very important. This is something that could potentially happen if you're writing some banking code. And I know that some of you are doing that in your Java class right now, but this is slightly different. We're going to assume that we have kind of a multi-threaded program. So we have a banking system that has two methods, a deposit and a withdraw. These two methods are past the amount that's supposed to be deposited or withdrawn. Assume that there's a husband and wife who share this bank account, and that at one point the husband decides to withdraw money at the same time the wife is depositing money. Your problem here is to describe how a race condition is possible and what might be done to prevent the race condition from occurring. In other words, how could the results be different depending on exactly when the husband does the withdrawal and sees his account balance and when the wife does the deposit and sees her account balance? Okay, so I think this is a fairly simple problem if you understand how race conditions work. So I want you to describe how the race condition is possible, and then what would you do? And this is important. Don't just describe the race condition, but also include what you might do to prevent the race condition from occurring. So that's going to be an important part of this assignment. Don't just explain the race condition, but also talk about how it might happen. Okay, Hala has a question. Do you mean we should explain two cases that might happen? Yes, that would be a good way to do it. Show how in one case the husband sees one balance and the wife sees a different one, and vice versa. Okay? And then Sarah says, answer it as steps. Yes, for describing how a race condition is possible, describing what could happen in steps would be a good way to do it. You don't have to do it in steps, but that would certainly make it clear, kind of like I showed you in the milk problem. Okay? Yeah, that's exactly, Sarah, like the milk example. But the other thing I want you to do is explain how you could have prevented the race condition from occurring. And that's something we haven't talked about yet, and we're going to talk about that now. Okay, the way we prevent race conditions from occurring is by having what's called a critical section. And in the critical section, you have a segment of code where the different threads or processes are changing variables, accessing shared files, updating shared data. So what you want to do is make sure that if one thread is in the critical section, none of the other threads are in there. Okay? So what you're doing is you want to protect this critical section. That's why it's called critical. This is the thing that has to be protected so we don't run into a race condition. So the problem we have is to design code that processes use to communicate so that we don't have a race condition. And the way we do this is by requiring that each process ask permission to enter the critical section, and then they release the critical section when they're done with it and go on with the rest of their work. Okay, so what we're kind of doing is we're kind of locking this critical section so nobody else can access it until we're done with it. So we don't have this race condition where the results might be different. So I have a question for you. What is the critical section in the too much milk problem? What is the resource that we would need to protect to prevent that race condition? Any ideas? Okay, Hala said maybe synchronization would help, and that's exactly right. And that Nadia would wait. You know, you're both suggesting solutions to the problem. What is the critical section? What do we need to protect? What is it that both Nadia and Miriam shouldn't have access to at the same time? Okay. The answer here is that the critical section in the too much milk problem was the refrigerator. Okay, that's where the milk was. That's where you could think of the milk as the data that's changing. How much milk in the refrigerator is what's changing. And the refrigerator is what held that milk. So what if when Miriam came in and saw there wasn't milk, they did exactly what Fatima said. She locked the refrigerator. So when Nadia came home, she couldn't even get into the refrigerator to see whether there was extra milk or not. Okay, so that's what we're talking about with a critical section and how we would prevent a race condition by doing some locking. Okay, and we're going to talk about that. All right, so hopefully that makes it a little clear to you. So here's what a process would normally look like. A process would request to enter the critical section. When it's safe to enter the critical section, they would do that work, and then they would get out of the critical section, actually releasing any lock, and then do whatever work they needed to be done. So that's kind of one of the ways that processes are structured to avoid this race condition. We lock things before we enter a critical section, and we release the lock when we get out of the critical section. One way we can do a lock is with a mutex, a mutual exclusion lock. That's what mutex stands for, mutual exclusion. This simply means that if one process is in a section of code, the other process is excluded, and vice versa. It's mutually exclusive. A mutex is used to protect the critical section and avoid race conditions. The process acquires the lock before entering the critical section and releases the lock when it's done. And here's kind of what the code might look like. And again, this is just pseudocode. The main thread or the threads would acquire a lock before they got into the critical section, release the lock when they got out, and then do the remainder of their work. So what does the acquire do? It really is just a switch to say whether the critical section is available or not. And when it acquires the lock, oh, I have an extra semicolon in there, sorry about that. When it acquires the lock, it flips the switch to say, now I've locked the critical section. When it's done with the critical section, it releases the lock by making the available flag true. Okay? So that's all that's being done here. One of the things to notice here, though, is if the lock is not available, it's in what's called a busy wait here. If it's waiting for another process to release the lock, so the lock is not available, it's in this busy wait section. I'm waiting and waiting and waiting, doing this over and over and over in a loop. Okay, is this a situation when the end user tries to update the same data? Yes, that could cause, two end users, right, I got it. That could cause a race condition if you don't have that locking. You know, I've noticed this actually when I'm grading your assignments, sometimes I have your assignment open and I'm grading it, And then I try to do something else with that assignment, like upload it, and it tells me, you can't do that. Somebody else is using it. That's because the resource is locked. Okay, so it's a similar kind of situation. So Holly, you're correct. In this critical section, that's where the update to the data would be. Okay, in the critical section. So even if you think about your homework problem with going to the bank, it's actually, you know, when the deposit or the withdraw is updating that bank balance, that's what's in the critical section. Because depending on who updates the bank balance first, the bank balance could be different. So as soon as the one tries to update the bank balance, you want to lock out the other one from updating that bank balance. Does that answer your question, Hala? So we're just using these locks, this acquire and release of the lock, to prevent that race condition from occurring. Okay? The problem with the mutexes is that there is this busy wait, so we're kind of wasting the CPU's time. So people came up with a different tool called a semaphore that doesn't require the busy waiting. Okay, sometimes it does, sometimes it doesn't, but it could potentially not require the busy waiting, and I'll explain a little bit about that. So again, a semaphore is like an integer value. And we could have binary semaphores, which are just like mutexes, kind of a flag that's on or off, or a counting semaphore. And with a counting semaphore, you're actually counting how many resources are available, and so you keep decreasing or increasing the count as somebody uses one of the resources. And so that assumes that there's multiple resources available, and different processes can be accessing the different resources that are shared. We need to have atomic operations to modify the semaphore. Okay, we have to make sure that when we're changing this semaphore, no other process can get in. That's why it's called, excuse me, that's why it's called an atomic operation. The hardware won't let you interrupt this operation, the operation for the wait and the signal, because they're the operations that are changing the semaphore. Okay, so you're not actually going to be writing the wait and signal commands themselves, but you will be using something like a wait and a signal, and we'll talk about that more later. The way we can prevent the busy wait, remember I said a semaphore, if it's written like we see here, still has a busy wait in it. In order to prevent the busy wait, a signal can actually remove a process from a list and wake it up. In other words, if we want to do a semaphore, what we could do is, instead of having the process that's waiting sit there and say, is the resource available yet? Is the resource available yet? Is the resource available yet? In doing that over and over and over, one way that it could be implemented is when a process can't get access to a resource, can't get access to that critical section, they're just put on a waiting list and they go to sleep. Okay, they say, oh, I know it's not available, I'm going to go on a waiting list and go to sleep. Then when the other process that had access to the critical section is done, what they do is they remove the process from the waiting list and wake it up. Say, okay, it's your turn, I'm done. Okay, so that's how semaphores can be implemented to solve the critical section problem. All right. Another option is a monitor, and this is kind of a similar idea in that you have all the operations that are critical, and you have your shared data, and the monitor is a way to ensure mutual exclusion of the operations and data within the monitor. So in our other case, with mutexes or semaphores, the programmer had to actually say, give me the lock to the critical section, and I'm going to release the lock to the critical section. In a monitor, all the process needs to do is say, oh, I want to access these operations here, and they're not going to be allowed to enter the monitor, and they'll be put on a queue. Okay? So they'll get queued up whenever someone is already inside the monitor. Okay, so it's just a slightly different way of solving this other problem. Monitors could have condition variables on them, and these will allow the thread to block until a certain condition becomes true. So again, rather than these going into some kind of loop where they're checking or whatever, they can just block, say, you know, I'm just going to sit here waiting until I know something has happened and I can probably get into the monitor, and so they'll just be blocked until that happens. And that's how the monitors work with the condition variables. So it's all kind of the same idea. We just want to protect these resources so that two threads aren't accessing them at the same time. Your book goes into a number of classic synchronization problems. There's the bounded buffer problem, there's the readers and writers problem, and there's the dining philosophers problem. And these are all classic computer science problems where synchronization can be an issue. And so usually when someone comes up with a new idea, like originally there were just mutexes and they didn't work so well, so somebody came up with the idea of semaphores, and then somebody came up with the idea of monitors, and all these different ways that people are coming up with ways to kind of lock resources so that other processes can't access them. These problems, the bounded buffer problem, the reader and writers problem, and the dining philosophers problem are classic computer science problems that people use to kind of prove that their solution will prevent the synchronization problems. Okay, you're going to be looking at this type of thing in your project. And I kind of went through this project in the office hours yesterday. So if you didn't attend the office hours, I would recommend that you listen to the recording, because I walked through this whole thing. Remember that we're going to use Java threads. We're going to write this in Java, not C. We're going to use Java threads to implement this. And I gave you some ideas about how you can start on this programming problem. Okay, so the charts I'm paging through right here are just the problem as it was stated in your book, except I made the change to say we're going to use Java threads, not P threads. Okay, so I have some tips for you to get started on this. And I know, I've seen, thanks to Sarah, she gave me some examples of what you had been asked to do as far as coding in your earlier Java course, your first Java course. So I kind of have a feel for, what you've done or haven't done in the course, depending on when you took the course or if you did additional programming outside of that course. So I want to give you some tips to get you started. And one of the tips I talked about yesterday is identify the possible classes and methods. And you could do this by reading the problem statement and looking for the nouns and the verbs. And I talked about this yesterday. The other thing that I would do is I wouldn't get to writing code in Java right away. Usually what I try to do is I write pseudocode. I write it in pencil and paper, or I type it in a Word document, just something so that I can get my thoughts down on paper without worrying about, oh, what classes should I be using? Do I need a semicolon here? Where do I put the bracket? Okay, just write the pseudocode to get your logic down. Okay, so I would recommend that. The next thing I would do is walk through your logic until you're pretty certain it is correct. And what I usually do here is I actually talk to myself when I'm doing this. Okay? I talk to myself, I go through my logic and say, okay, now at this step it's going to do this, at this step it's going to do this, and I draw little pictures and whatever I need to do to go through the code in my head to understand whether or not it's doing what it's supposed to be doing. And I would recommend that you spend quite a bit of time on these first couple steps before you ever open BlueJ and try to write some Java code. Another thing that I've done to help me then go from my pseudocode to the Java code is sometimes I take my pseudocode and I put it in a class in BlueJ, in my classes in BlueJ. I create my classes and I put my pseudocode in as comments. Okay, so this will remind me what I expect to do. Every line of pseudocode, I make a separate comment in my Java class. So I might have no Java code in the class at all, but I will have the comments that are going to remind me what it was I wanted to do in this class. And then I might start writing the code. But don't start to write the code too soon. Okay, I know you're all anxious about your Java and how well you can program in Java and whatever, but it's really much, much more important that you get the logic correct before you start writing the code. I can't stress this enough. Work on the logic, not the code, and then we can work on the code later. Okay, so that's how I would recommend that you get started on this. If you are worrying about the code, I had posted on the resources a link to a tutorial on doing concurrency in Java, okay? And then I gave you a suggestion. You might want to, once you read this, it'll make more sense once you go through that tutorial, but you might want to subclass threads instead of implementing runnable. In real life, you're probably going to be implementing runnable because that gives you a lot more flexibility. Here in a student situation, I would think you want to subclass threads because it's a little simpler to do. Okay, and once you become an experienced Java programmer, you'll know whether to use runnable or use thread, and you'll understand the differences. But I know some of you are just learning what an interface is and how you use interfaces, and that's what runnable is, whereas thread is a class that you can just subclass and do what you need to do. Now, we can talk about the programming assignment more in next week's office hours, okay? And I know some of you have scheduling conflicts and you can't make the office hours, but what I'm going to try to do is go through this. Remember that your program isn't due until the end of week 6, so you have some time to do it. And what I want to do is work through some of this with you in the office hours. Okay, because I know you have very limited programming experience, and I'm going to start working with you through developing your logic and developing code in the office hours. Also, if you do what I suggested and you write pseudocode and you put it in there as comments and you never get your Java code to run, understanding what your logic was, whether you could figure out how to do it in Java or not, is more important than getting the exact code to work. Okay? So when you turn in your programming assignment, I'm going to be reading your comments and seeing what you thought this code was going to do, and not just look at, oh, does it run or doesn't it run? Okay, I'll go through it line by line when I grade it. And I will take what you say in your comments into account, because I know you may not be able to get this to run given your programming experience, but you should be able to develop the logic. Okay, we're out of time for today. As usual, I'm going to continue through these and talk about the deadlocks, and I'll go through that fairly quickly. But if you have to leave, I totally understand. Okay, but I just wanted to get you started on the programming assignment, and you do have another exercise which I'll talk about later in this session. So if you have to leave now, just make sure you come back and look at the recording once it's out there, and just skip to where you left off. Okay. All right, so I'm going to continue along even though I know a lot of you have to leave. So the next thing your book talks about is deadlocks. And when you think about it, we're in a situation where we could potentially have race conditions, so we're locking resources. We're locking those critical sections so that two threads aren't accessing resources at the same time. So what we have is a situation where multiple processes are going after a limited number of resources. If a resource isn't available, the process will wait. Okay, and that's what we saw. Okay, Hala had a question about the programming assignment. Can we send you the pseudocode first, or should we submit the pseudocode and the runnable code together? Just submit them together. Okay, just put the pseudocode in your comments and submit your code. Okay, and we'll be talking about pseudocode, and I'll help you with that some in the office hours. Okay? So yes, I don't need the pseudocode submitted separately. Okay, to get back to the deadlocks. The problem is if a resource isn't available, the process will wait. But if the process that's holding the resource that the second process wants, if that's waiting for something else, you have a deadlock situation. Okay, so if one process has a resource and another one wants it, and the process that has the resource is also waiting for somebody else to release a process, that process that's holding a resource can also be waiting, and so you're in a deadlock situation. So eventually, in a system, if you get too many things in a deadlock situation, you're going to eventually run out of processes in your system. Okay, because all the processes are going to get backed up, waiting and waiting and waiting, and eventually the system just won't even start any new processes anymore, and your system will lock up and you'll have to reboot and so forth. Okay, so what we want to do is try to avoid or prevent deadlocks. Okay. So there are certain conditions for a deadlock. The conditions for a deadlock are mutual exclusion, which means that only one process can use a resource at a time, hold and wait, and this is the condition that occurs when a process is holding a resource and is waiting to acquire a resource held by another process, and there's no preemption. In other words, nobody is going to force a process to release the resource that it's holding, and there's a circular wait. And this is where P0 is waiting for a resource that is held by P1, P1 is waiting for a resource that's held by P2, all the way up to Pn-1, where Pn-1 is waiting for a resource that's held by Pn, and the last process is waiting for a resource that's held by the first process. So you have everybody's waiting for something somebody else has. Okay? So if you get into this condition, you're going to have a deadlock. So the way we prevent or avoid deadlocks is to try to set the system up so that one of these conditions does not hold. Because if all of them hold, you have a deadlock. So we try to make the system so that only one of the conditions holds. Okay, so deadlock prevention is a way of ensuring at least one of the conditions for a deadlock cannot hold. We know we have to have mutual exclusion. We need mutual exclusion so we don't get into a race condition. Okay, so mutual exclusion is always going to hold. We're always going to have that condition. So we have to look at the other three and say, could we prevent those? Now we can prevent a hold and wait situation, because in a hold and wait situation, what we can do is we can have the processes to request and be allocated all their resources before they start. So they can't be holding something and be waiting for something else, because they won't even get started unless they have everything they need. Okay? It's kind of like, you know, when you're making food, when you're making a recipe. Okay, you might want to make sure you have all the ingredients before you even start on that recipe. Okay, and that's how we could prevent a hold and wait. Okay, so let's say that, for instance, to use the recipe analogy, let's say, for instance, in a normal situation, I'm using the mixer and I'm going to need the oven when I'm cooking. My husband's making something at the same time, and he's already preheating the oven, but he needs the mixer. Okay, neither one of us is going to be able to get our recipe done. But if I implement a hold and wait prevention scenario, what I can do is say, I'm not going to start my recipe until I'm sure I have both the mixer and the oven. Or my husband can say he's not going to start his recipe until he has both the mixer and the oven. And so one of us will just wait for the other guy to be done, and we won't have a deadlock. Okay? The other way you can prevent a hold and wait is by saying a process can only request resources when it has none. So in the recipe example, I can only request both the oven and the mixer if I don't have any resources. Okay? If I already have the mixer, I can't request the oven, and vice versa. Okay? So it's kind of, I have to be able to get them all, or I don't get any of them. Okay? So that's another way we could prevent a hold and wait condition and thereby prevent a deadlock. The condition of no preemption, the easiest way to prevent no preemption is allow there to be preemption. Okay? And so if a resource if a process that's holding a resource requests one that can't be allocated, then we can force it to release all its other resources, because somebody else might be waiting for them. Another way we can preempt is that if a process is holding a resource and another process asks for that resource, the second process can force the first process to release its resources. Okay? But doing this forcing means that we're preempting it. We're allowing one process to get in there and force the other one to give up its resources and get out of or release the CPU. Okay? So that's one thing that's sometimes done to help prevent deadlocks. Another thing that we could do is impose an order on the resources. In other words, let's say that we have memory to be allocated, we have the CPU to be allocated, we have files to be allocated. These are all resources that can be acquired. So let's say that we say, okay, the first thing that you have to do is make sure that you have enough memory to run. Okay? The next thing we want to do is make sure that the files are available. And then the last thing we're going to do is make sure the CPU is available. So each process is going to be forced to make sure it has all the files that it needs, or all the memory that it needs, before it goes looking to see if it has all the files that it needs. And it'll do that before it goes looking to see if the CPU is available. By forcing all of them to go in this order, we know that that we're not going to get into a deadlock situation, because if the first process grabs, the file, it's going to then move on and grab memory. The second process won't be able to grab the files it needs, so it's not going to be grabbing any of the other resources that the first process needed. And so we've actually prevented a deadlock by preventing that circular wait condition. We can also try to avoid deadlocks. In order to avoid deadlocks, the operating system has to know ahead of time what resources a process will request and use. Okay? So that way the operating system could decide whether or not to give a process the resources depending on what resources are currently available, what resources are allocated to each process, and what's going to happen in the future. Since the operating system knows who's using what resources and when, the operating system can come up with an algorithm that's going to avoid deadlocks, because it won't give resources to a process if giving it the resource is going to cause a deadlock situation. So that's a deadlock avoidance. If you can't prevent deadlocks and you can't avoid deadlocks, the best you can do is detect that they happen and try to recover from it. Okay? So this is another thing that operating systems do, is they try to detect that a deadlock has occurred. Okay, the operating system notices that there are a lot of processes waiting, and it tries to detect that a deadlock has occurred, and then it might make a decision to force a process to release resources, to stop a process from running, to do something to break that deadlock. Okay? And it's not always something nice. It may just cancel a job that was deadlocked. Okay? Now, if you don't have these algorithms to detect a deadlock or to recover from a deadlock, and you don't have algorithms for deadlock prevention or deadlock avoidance, the system is going to deteriorate eventually, because processes may get deadlocked. When the system performance deteriorates, it means that processes are waiting and waiting. New processes come into the system. They're waiting. Everybody's waiting. Your performance is really bad because no one is being allocated resources. Eventually, your system locks up and has to be restarted. Okay? Unfortunately, most operating systems use this approach. They don't have deadlock prevention, they don't have deadlock avoidance, they don't have deadlock detection and recovery. What happens is that deadlocks just occur, your system performance deteriorates, and eventually the processes or the system might crash. So my question to you is, why wouldn't an operating system implement deadlock prevention or deadlock avoidance or deadlock detection and recovery? Okay, why do we have all these operating systems that they just let these crashes occur? Any ideas? Okay, usually when Amal says because there's a lot of threads in the system. Okay, that's true. And I think what you're getting at, Amal, is that there might be a lot of threads in the system, and it's actually very difficult to actually implement these kind of detection prevention, detection avoidance, or deadlock detection and recovery schemes. Okay, so even though we have, the reality is, just to let you know, even though we have a lot of threads running, deadlocks actually occur fairly infrequently. They really don't occur as often as you think they would, because programmers are fairly careful about doing things like using semaphores and so forth to lock resources, to avoid race conditions, but they also are aware often what's going on in the other threads in their own code, so they can avoid deadlock conditions. And the truth of the matter is, there might be one true deadlock condition in a year, even though we have all these threads going on. It just happens that they're not all accessing the same resource at the same time in most general purpose operating systems. Everybody's doing different things on the system, so we're not seeing the deadlocks occurring as frequently as you might think. The other thing is that just letting the system crash is cheaper than handling the deadlocks. Doing any of these things is fairly expensive. Okay, writing this code and having it in the operating system, and the CPU usage that's taken up by trying to detect these deadlock conditions and whatever, all this is very expensive. So it's actually cheaper for the operating system to say, I'm just going to ignore it, so the system crashes every once in a while, who cares? Okay? The other thing is that, sometimes there's other methods that you could use to recover from a deadlock. Okay, for instance, I might be running a process. Let's say I'm writing my own threads, I'm writing my Java code, and I wrote it poorly. And what's happening when I run my Java code is that I've deadlocked my processes, my threads. Okay, when I'm sitting there forever and my job is never ending, what I just do is I go out to my task manager and I kill that job. Okay, I've actually eliminated the deadlock because I killed my own job. I killed my process. All right, and that's simple enough to do. Okay. Hala says, I think database administration software handles these types of deadlocks. Yet, when you're working in a database, when you're working in any kind of file system, there is file locking. Okay, and file locking is a little bit different from when we're talking about processes being deadlocked. Okay, so one of the things that we try to do with files and with databases, which are just types of files, is avoid a deadlock for the file locking, but remember that processes are locking all kinds of resources. They're locking memory, they're locking, their access to the CPU, they're locking, different devices and so forth. And so what you're looking at is really just a more bounded problem. And sometimes if the database administration software isn't written too well, you can still run into problems. But for the most part, you won't. Okay? Very good point, Hala. Okay, so here we get to question 7. Or exercise 7.7, and again here this is a little bit simpler question than what was originally assigned. And this says, consider a system consisting of 4 resources of the same type that are shared by 3 processes, each of which needs at most 2 resources. Show that the system is deadlock free. And what you want to do, and again, explain your answer, explain it to me as best you can, why a deadlock wouldn't occur. And the key thing to realize here is that, kind of look at how would a deadlock occur. Okay, let's assume that a deadlock has occurred in this system, and in order for that to happen, what are the conditions? Okay, and if you can't come up with conditions where a deadlock would occur, then the system is deadlock free. Okay, so if we have 3 processes and 4 resources, try to draw pictures, do whatever you can to look at, okay, I have 4 resources, and let's say, process 1 is holding resource 1 and 2, okay, because it can only hold up to 2. Let's say that process 2 needs resource 2 and resource 3. It's going to be waiting. If process 3 needs resource 3 and resource 4, it's going to be waiting. Okay? But is it deadlocked? Okay? So kind of work through some of that and then explain an example to me that shows why the system won't deadlock. You're trying to show that the system is deadlock free. Okay, so again, just kind of play around with it a little. What I did when I solved this is I drew little pictures, and I had little boxes that were my resources, and I had little boxes that were my processes, and I drew lines between them, and I did solid lines. If a process was holding a resource, it was allocated that resource, and I did little dashed lines to show that a process was waiting for a resource, and I just went through that and came up with the answer. So that's kind of a way that you can look at this problem. Okay, any questions on what you need to do here? Okay. Okay, well that's all I had for today. I hope that was helpful to you. Hala asked if you should include a drawing and an explanation. It wouldn't hurt to do both. If you've done the drawing, it may be, I know some of you struggle in your assignments to find the right words to say. And so if you show me a drawing and then write the words, I can look at your drawing and see what you're talking about perhaps more easily than I can figure it out without the drawing. Okay, so I'm not requiring that you do a drawing and an explanation, but it helps if you do it. Any other questions? Okay, if there are no further questions, I'm going to end the session for today. If you do have any questions, please feel free to email me. Also, I just want to remind you that next Tuesday I will be holding office hours, and I will answer any questions people have about our week 5 reading in the office hours. But if there are no questions about that, I plan to talk about your programming assignment and actually work through some of that with you. Okay? So I'm going to try to help you in the office hours, and if you can't make it, just try to watch the recordings. Okay, so thank you, and